start the first session. My name is Pramod. I come from Ramanujan Research Institute. And so the first talk today is by Mangal Chandra Mahato. And the topic is Stochastic Resonance and Ratchet Effects in Sinusoidal Potential, Numerical and some Experimental Results. So today we have to be super strict because there is a special program starting immediately after this session. So let's try to stick to time.
Before I begin, let me thank the organizers for inviting me to this meeting. Yes, it's not working.
Hello.
So as is clear, my topic is displayed as there. My collaborators are Miss Rinborn and Ivan Stem Saukme. The first collaborator, she used to be my student. Now she is working at NIT Shillong. Other one is my PhD student. Basically, I'll solve this Langevin equation. If I remove that xi there, the noise term, it is basically a damped pendulum. Not only damped, it is also forced. So this one cannot be solved theoretically, analytically. So what I do is that I solve it numerically first, and then I'll show you some results of some analog simulation experiments just to solve it. So what I do is that I just write it down in dimensionless form, which looks like this. Here the potential is not really harmonic. This is sinusoidal. So you can see that the potential is basically periodic, and if you apply some force, say constant force, then the potential it has got some effective slope. Here the amplitude of this oscillatory force is small, is 0.2, so that as you can see that the potential barrier remains there. It's about 10% of the potential barrier. So why do I study it? Basically, I want to study stochastic resonance in periodic potentials, especially this sinusoidal potential. Stochastic resonance has been seen essentially in bistable system, but not in periodic potential system. So our work will be to see whether we can see that, and also our plan was to show that in this kind of system one can see a ratchet effect also simultaneously, but I'll not go into all those details. The results are published here in PRE. I'll go over directly to the results. Here the result, you can see that the black one is basically the forcing, no, the blue one is the forcing, this F, and the black one is the trajectory of the particle. You can see that this trajectory is almost in phase and the amplitude is small. I can see another one where you can see that the trajectory has got a very large amplitude and the phase difference is also quite large. These two solutions I can get just by using various initial conditions. I have to solve I solve this equation. In order to solve it numerically or in analog simulation, I have to take initial conditions, position as well as the velocity. Velocity we take to be 0, and initial condition, as you can see that since the potential is sinusoidal, the initial position I can start from -pi to +pi, anywhere I can do. So if I choose these initial conditions, we can get these two solutions. These are the only two solutions we can see. So what I am saying is that I have got a pendulum. I just drive it. The drive amplitude is small, so that it just oscillates in a well. Given an initial condition, I get either this solution or the small amplitude or the large amplitude state. These are the only two states you can get. Since this F0 is small, you can see that here, if I take the initial condition as shown here, initial condition from -0.5 to +0.5, for example, I can see that these states, they occur here. For example, this is the phase is small, this here the phase is large, and the amplitude is also large. So these are the only two phases I can see. So from here I can see that these two states are basically the dynamical states of our system. These two I want to see by using this analog simulation. Here you can see that I have got a block diagram. In this block diagram, I have written down the equation here. This equation is exactly similar to what I had started with. So I just solve it. If I solve it, I have taken various parameters. Using those parameters, I can see that here I have got a tau, that is basically the period of the driving force, and this one gamma is the damping coefficient. So correspondingly, I have got various frequencies, and I can see that this is our experimental setup. Here also I can see a similar states, one which has got a large amplitude, another one a small amplitude. These are the photographs or the outputs from the oscillator. Here the important thing is that this is numerical. These solutions I can get not everywhere, but these are restricted here. For example, I can take this gamma which varies from say 0.7 to 0.16, and tau which essentially varies from about 7.5 to 10 only. And if you go beyond, you can will see that this side I can get only the small amplitude phase. If I go down, I can get only the large amplitude phase. Here in this region, I can get both small amplitude as well as the large amplitude. So this is essentially, if I start from some initial condition, either I get the small amplitude phase or I can get the large amplitude phase. And if I go beyond this gamma equal to say 0.16, you can see that these two phases, they go continuously from small amplitude to large amplitude. There is no transition. Here these two phases are important just because that if this result that I am showing is for when the noise strength is 0. If I take the temperature to be non-zero, then what happens is that if I run the system, initially this large amplitude phase, this goes into a small amplitude phase. And then if you increase further, then all the large amplitude states, they go into the small amplitude state, and then on from small amplitude state also they go to the large amplitude phase. So this is essentially what I want to see, is that I can see here, for example, this is large amplitude phase, this is small amplitude phase. So even though the potential is periodic, I can see that the motion of the particle or the motion of pendulum, I can see that they can be written as a bistable system. Even though the potential is multistable sinusoidal, these trajectories, they are either having a large amplitude phase or a small amplitude. So these are the two states I can get. So why do we want to go into these two amplitude states? It's just because this is very much convenient for me to explain why should stochastic resonance take place in a periodic potential system. It has earlier been claimed, as I told you earlier, that stochastic resonance you can see only in a bistable system. But here we have gone over from a multistable system to a bistable system, in the sense that I have got just two states of trajectories, small amplitude and large amplitude. And if the temperature is increased further, for example, here the potential variation is small. So therefore, for small amplitude, for small noise strength, this large amplitude state, it goes into small amplitude state. But if you increase further, then small amplitude states, they can also go over to the large amplitude state. So from the minimum of the fraction of large amplitude state, the fraction increases gradually. And we see that if you increase the temperature further, after some time, the fraction becomes half, this is 0.5. Thereon, the distinction between these two states, they become really blurred. So we do not see any distinction between these two states. The essentially thing what I want to tell you is that this is the temperature at which these fractions become half, that the energy absorbed by the system, by the pendulum for example, it becomes the largest. If you increase further, the energy absorption, it actually decreases. That means that the energy absorption, which is basically the hysteresis loop area between, for example, in the case of circuitry, this is IV graph, or in case of a pendulum, for example, this is theta versus the drive field. Here, this is also, this energy absorbed by the system is essentially a measure of the stochastic resonance. This is actually equivalent to saying that the signal to noise ratio becomes maximum at the temperature where you say that the stochastic resonance is taking place. Stochastic resonance, basically one would say that this is essentially the system, the output of the system. If you give a small amplitude input, the output becomes more coherent at that temperature. So that means that the noise essentially helps in getting a better signal, output signal, than when the temperature is lower. So here, these are basically numerical results. Here you can see that the amplitude of this signal with tau, it goes like this. Here there is a discontinuity, here there is a discontinuity, but if you say gamma equal to 0.17, there is this is continuously it goes there. Here this is the result obtained by this analog simulation. Doing this experiment, there are a lot of difficulties. Actually, I have started this, learning this.
About 40 seconds more and then we have one question.
Okay, I'll just be through. Here the difficulty is that to solve this equation, I need to have some input condition, initial condition that is very difficult to do there. And also there are other difficulties about this sine function, getting sine function. So I have got some x, for example, I want to get sine of x. I'm still facing difficulty. Hopefully, I'll solve them. So I thank you very much.
Okay, it's time for one or two questions.
States like the low amplitude and the large amplitude states have the same qualities and they are not very different. But
no, they're still different. They're still different. But if you increase the temperature further, the distinction becomes really blurred. They're no longer different.
But that's what I was saying. The states are the same. The probabilities may be equal or unequal. Sorry, the states are not the same whether the probabilities are equal or not equal.
So probably after as I said, that after if you increase the temperature further, these states, I cannot say that it is in this state or that other state. They have become almost indistinguishable.
The system makes a transition between the two states.
Yes.
Okay, maybe in the interest of time, we move on to the next speaker. So let's thank Mangal once again.